Hello, my CFA friends. How are you, my friends? Today, I want to try something different. I want to offer you a complete module from my question-based revision, completely free of charge, so that you can have a look at it, try the questions, pause the video, try the questions, see if you like it, and hopefully realize that it is something that's going to genuinely help you prepare for this exam. So I want to show it to you. But before we get into it, I just want to make a couple of points. Firstly, a Fiverr is nothing these days, guys. Now, I know you're going to tell me, Martin, you live in London. It's a uber expensive city. And unfortunately, you are correct. I could probably buy a coffee here with a Fiverr. I can hop on the tube, underground, train, subway, whatever you want to call it. And that's about as far as a Fiverr will get me. Now, you may be living in India. It's cheaper there, of course. But guys, have you actually seen what's happening to global money supply? We sailed through the previous all-time high at the end of July, early August. So basically, a couple of months ago, and we are now above the all-time high in an uncharted territory. Guys, my point is a Fiverr is nothing, no matter where you're located around the world. Inflation is coming for all of us. The global money printer is going brrr. And the second point I want to make, my friends, is please don't make me go on my main competitors' websites to show you their prices and to show you how much I have saved you by providing a completely free of charge, complete CFA Level 1 tuition course, and now a revision course. Give my revision course a try. Here it is. This is my website. You can see here, stoyanov.co.uk. You can see the reviews of previous students, happy students. If you like my course, please DM me, email me, and I'm more than happy to add your review to the website as well. Guys, if I wanted to make a lot of money, I'd be working for a major corporate right now. I won't be recording free YouTube videos, okay? So you can be sure I'm not here to make a lot of money. I am here because I genuinely want to help all of you. I want to bring my top quality education to every living room and kitchen around the world, okay? That's what I want to do. Obviously, every living room and kitchen that is interested in finance education / CFA education, okay? But that's my goal. However, guys, reality check, I have bills to pay, okay? So I need your support. So my friends, don't be shy. Give my course a try. It's stoyanov.co.uk. And now let's have a look at one of the modules completely free of charge for the entire community. Welcome to our module on hypothesis testing. Now, I know you've been waiting for this module, my friends, because hypothesis testing is really up there on the worry list of the candidates. So don't worry, I'm going to be illustrating all the key concepts here, all the key tests. So let's get started. Make sure you're pausing the videos. Make sure you are attempting all these questions yourselves, my friends. Okay. So we've got a trader who wants to test the null hypothesis that a particular trading strategy is consistent with a monthly return of 1.3% at the 95% confidence level. So a couple of things to unpack here. First of all, what do we mean by consistent with? That wording, sometimes you might encounter it. Well, we are saying that essentially we have a null hypothesis, so H0. And effectively, what we are saying is that the mean that this trader believes we have for this trading strategy is consistent with or equal to 1.3%. So that is your null hypothesis. Therefore, the alternative hypothesis is mu is different from 1.3%. And immediately here, you can see this is going to be a two-tailed test. Okay, so when you've got equal to different from, this is always going to be a two-tailed test. Also, we should be aware of what that means. Couple of ways this can get tested. Either they're going to tell you 95% confidence level, or they could tell you 5% significance level, and often that is denoted as our alpha. So the alpha is the probability in the rejection tails. So the trader has collected a sample, 35 monthly returns, good. Calculated a sample mean, so that is your N. Sample mean, that is your X bar. And sample standard deviation, that is your S. Remember, sigma is population, S is a sample. Now, when you're performing a hypothesis test, there are a couple of things you need to do. First, you need to have a computed statistic. For this test, the computed statistic is going to be a T statistic. And it's quite reminiscent of the structure X minus mu over sigma. But the difference here is because we are sampling, we will have X bar minus mu over S square root N. So notice here the denominator is our standard error. So X bar we've got as 2, right? So this is your X bar, this is your mu, this is your hypothesized mean. Your sample standard deviation is 1.8, and then we're dividing by the square root of 35. So go ahead now and tell me what you get for that. So hopefully you got 2.3. This represents our computed statistic. So basically the bulk of the work was the computed stat. The other part is to figure out the critical T statistic. The examiner will give us some sort of a snippet of a table. So the easy win here is if you know your sample size is 35, how many degrees of freedom are you gonna have? So you're gonna lose 1 degree of freedom, DOF. We lose 1 degree of freedom, 35. Take away 1 is 34. So we're gonna be in the first row of the table. And then the slightly trickier bit is to figure out which column we wanna be in. So here you got to be very careful what kind of significance they're giving you. Are they telling you the total significance or the significance just in one tail? So as you can see here, we're given the probability in just one tail as being either 2.5 or 5%. Now, we got to remember a couple of things. We know our total significance is 5%. And we know that it is a two-tailed test because we're using equals and different from. Remember, that all relates to that initial wording of consistent with, which means equal to. So because we've got two tails, because we've got a significance of 5%, we're going to split that over two tails. So each tail will have 2.5%. So that means this column is a red herring. And that means that our critical value, therefore, is 2.032. So how do we proceed from here? Well, we have to remember that we reject whenever the computed value is greater than the critical. And let me just go to the whiteboard here to visualize that. So, okay, I've got my bell-shaped distribution. I've got my critical value of, let's say, around 2. And I also have my computed value of 2.30. So can you see that this being your rejection tail, your computed value is in the rejection tail. So basically the rule is reject the null hypothesis if the computed statistic exceeds the critical statistic. And therefore, in this case, we are going to be rejecting the null. So, fail to reject, definitely not true. Remember, in statistics, we don't accept, we cannot accept the null, but we can fail to reject it. Reject based on a computed statistic of 2.30. Well, yes, that is our computed stat. So that sounds like a right answer. Just to rule out C, reject based on a computed stat of 657. Well, that's not true at all. So we can circle B and move on. A trader wishes to perform a hypothesis test that a particular trading strategy generates positive returns at the 5% significance level. So notice here how we've shaken things a little bit. So firstly, instead of giving you confidence level, this time we're giving you the significance level. So this is the probability in the rejection tails directly. But also notice here the wording, trading strategy that generates positive returns. So we are not saying a trading strategy that has non-zero returns, which would imply positive or negative. We're saying we're only interested in positive returns. One thing you got to remember from my tuition videos is that the null hypothesis must include the equal sign. So the null will be less than or equal to 0. And the alternative here is what we are going for. The mean is greater than 0. Immediately here, when you've got wording like less than or greater than, you must be thinking one-tailed test. Very, very important when we come down to the table for the critical value. So again, we've got a sample size. Let's mark that as N. We also have a sample mean here and a sample standard deviation. So let's mark that as an X bar and also as an S, sample standard deviation. Okay. The analyst is most likely to reject based on a certain computed value, or fail to reject based on a certain critical, or fail to reject based on a computed value. Okay, so let's get started. Again, we want to compute the T statistic. We know it's X bar minus mu over S square root N. So this part of the challenge will be very similar to what we did earlier. So 0.41, take away the hypothesized value this time of 0, because we're basically saying the now is less than or equal to 0. Then the sample standard deviation is 135, and we're dividing by the square root of sample size 38. Again, go ahead and calculate that for me. And that's hopefully coming at 1.87 for you, my friends. Okay, and then we're coming down to this table. We have to lose 1 degree of freedom, and minus 1. So we're going to be again in the first row here, 37. And then we have to read this carefully. Probability in one tail 250 or 5%. Well, we are performing a test at the 5% significant, but this time this is a one tail test. So we want all of that 5% to reside in the right tail. So this time column 1 is the red herring and column 2 is the correct column. So we need 37 degrees of freedom, 5% significance in the right tail. That is going to give me a critical value of 1687. And so again, I would say reject the null, and therefore our trader will conclude that this particular trading strategy does generate positive return. And that's because the computed stat, which is 1.87, is greater than the critical stat, which was 1687. Okay, so that's why we are going to be rejecting the null. Let's have a look. So reject based on a computed stat of 187. That sounds like the right answer. Fail to reject, fail to reject. We can eliminate those options because you will fail to reject only if your computed stat is lower than the critical stat. An index has generated a mean monthly return of 2% over the past 1.5 years. So key point here, it's monthly returns we're talking about. Standard deviation of monthly returns has been 3% over the same period. The analyst has formulated a null hypothesis at the 5% level that monthly volatility should be equal to or greater than 3.5%. The analyst is most likely to reject, fail to reject. Okay, so first thing here, you need to figure out what sort of test am I performing? Is it going to be a z-test, t-test, chi-squared, f-test? What sort of test is it? So remember, a test on volatility is a test on standard deviation. When you are testing a single standard deviation, you're in the world of the chi-squared test. So we don't actually need the mean monthly return because the test is on the standard deviation. We have 1.5 years worth of monthly data, so 1.5 times 12 will give me a sample size of 18 months. The standard deviation of monthly return has been 3% over that period, so that implies that this is a sample standard deviation. And then you have hypothesized a null. Let's have a look that the volatility is equal to or greater than 350. So volatility equal to or greater than 350, that is your null. So your alternative that you're trying to essentially prove is that the volatility is less than 350. In fact, your sample volatility is less than 350, but we need to see if that is statistically true. So you know the drill. You're going to have a couple of things to do here. First, computed chi-squared, then critical chi-squared. So for the computed chi-squared, you must remember that you take the degrees of freedom times the sample standard deviation squared, or sample variance really, over hypothesized variance. So we've got 18 months, so that's 17 degrees of freedom, times the sample deviation squared over the hypothesized deviation squared. Okay, go ahead and calculate that. So I'm getting 1249, that is our computed value, and now we need to check whether this value is in a rejection tail. Enter the chi-squared critical values. Degrees of freedom, I'm sure you know the drill by now. We've got 18 sample size. That's going to give me 17 degrees of freedom. And this time, be careful, what they're giving me is the probability in the left tail of the distro. Do I want 250 or do I want 5%? We'll go back and check what sort of test are you performing. When you've got the wording greater than and less than, that is a one-tail test. So you want the entire 5% significance to be in the left tail. So that means this column is incorrect, and therefore we could say that the critical value is 8.672. Now be careful, I've had students who get confused here because they're saying, well, isn't the computed value greater than the critical and therefore we should reject? Okay, so be careful here, my friends. Let's go to the whiteboard and show you why that is not the case. So remember that chi-squared is bounded by 0 on the left. So, okay, well, that's not really how chi-squared looks because it's going to be asymmetric. It doesn't matter. So we are going to have our critical of, let's just go and see what it is, 8672, and that here represents the left rejection tail where you've got the 5%. Now our computed value is 1249, so 1249 is somewhere here. Now, yes, it's true that that value is greater than 8672, but is it in the rejection tail, my friends? And obviously, you can see visually it isn't. It is actually closer to the body, the main body of the distribution. So we are going to fail to reject. So just be very careful here with chi-squared tests when you're looking at the left tail because all the numbers are positive. And so you actually want the computed value to be below the critical in order for you to slip into the rejection tail. So going back here, we know that anything that's got the word reject is going to be wrong. We are going to be failing to reject. Is it going to be because we have a computed stat of 1249? Well, yes, that is true. And is it going to be failing to reject and concluding volatility is less than 350? Well, no, because failing to reject would mean that you stick with your null hypothesis, which says volatility is greater than or equal to 350. So we could rule out C, and therefore we can circle option Bravo. An analyst wishes to test the null hypothesis that the monthly standard deviation of returns of sample 1 exceeds that of sample 2 at the 5% significance level over the past 2 years. The two sample standard deviations are 2 and 1.5 respectively for samples 1 and 2. The analyst is most likely to fail to reject or reject. Okay, now again, pause, lean back, and think, what LOS are we being tested on? What sort of hypothesis test are we looking at? Is it Z, T, chi-squared, F? Well, chi-squared is one standard deviation or one variance test. F-test is when you're testing two variances. Now, the formula for the F-test is actually very, very easy. You just take the first variance, let's call it A, and you divide by the second variance, and you always make sure that the higher variance goes in the numerator so that your F-stat is greater than 1. Pretty easy if you ask me. So to compute the F, I just take 2 squared over 1.5 squared. So I've got a computed value of 178, and now I proceed down here to make sure that I also calculate the critical correctly. Okay, I do have 2 years worth of data, and it's monthly data. So there you go, the word monthly. So that means I've got a sample size of 24 for both sample 1 and sample 2. So again, I'm going to be looking for 23 degrees of freedom. And here, if you were given a proper F table, you will have one column for one set of degrees of freedom and the top row for the other set of degrees of freedom. Here we just basically know that it's 23 and 23. So we're going to be in the first row. And also here we need to think about whether it's a one-tailed or a two-tailed test. Immediately the word exceeds come to mind. So exceeds means that my alternative, let's just squeeze it here, the alternative is that the variance of sample 1 is greater than the variance of sample 2. That's what we are trying to show. So the null, therefore, would say that the variance of sample 1 is less than or equal to the variance of sample 2. And you can see immediately this is going to be a one-tailed test, and that 5% significance is going to be residing entirely in the right tail. So let's see then, I've got probability in right tail of 250, probability in right tail of 5. So hopefully you're thinking this is a red herring, and my critical value is 2.014. And again, we apply the same logic. Is the computed value of 178 greater than 2.04? So let's squeeze in a quick F table here. F is also only positive values because it's a ratio of squared numbers. But here we've got our critical, let's call it 2. Here I've got a rejection tail. And I'm asking myself, is the number 178 in the rejection tail? Well, no, it isn't. It's more towards the main body of the distribution. Therefore, I shall be failing to reject the null hypothesis. I shall be failing to state that the variance of sample 1 statistically exceeds the variance of sample 2. So I'm going to circle A, and these two options are going to be wrong. And finally, I want to conclude the module with a couple of wordy questions on the tests of two means. Now, I am making a conscious choice here not to test this mathematically because I think it is a very, very tedious calculation and a difficult formula to memorize. So I don't really believe the examiner will want to test this mathematically. I could be wrong, so if you are particularly worried about it, you can go to the Institute books and do a question or two on the test of two means, but I think I'm going to focus on what I believe are the more important points here, which are qualitative points. So, first question, an analyst is performing a hypothesis test to check if there is any difference in the mean monthly returns of stocks in the banking sector before and after a regulatory change. The test the analyst is least likely to perform is mean differences, paired comparisons test, or difference in means test. So, as you will have noticed when you studied this, there is a bit of game of words here. Obviously, we need a test on two means. And there are actually a couple of tests there, depending whether we can assume that the samples to be dependent or independent. If we assume independent, let's just write that, so independent samples, so uncorrelated samples, then we have difference in means test, that's the name. And if we assume dependent, then we have mean differences tests. So yeah, it does take a little bit of time to memorize these words. They're very similar. Mean difference test, and that is also known as the paired comparisons test. Okay, so a couple of names for the second test. Now, here the key point that you need to realize is that because we are looking at the same set of companies, the only thing that's changed is there's some new regulation. Well, of course, because it's the same set of companies, the two samples are obviously going to be correlated or dependent on each other. So the test that we do not want to use is the test where we're assuming independence, i.e. difference in means. So that's going to be our right answer because we don't want to use this test. Mean difference test, that is when the samples are dependent, where we have a dependent sample. And another way of stating that is that we're performing a paired comparisons test. Okay, and one final question on this test. When performing a test on the differences between two means and assuming independent samples with different individual sample variances, an analyst is most likely to use a t-test, and so sample size 1 plus sample size 2 minus 1 degrees of freedom, or a pooled estimate of the variances. Okay, so I'm not sure if you're finding this easy or difficult, but the easy win here is to just remember, hey, this is a t-test, so I know A is correct, but of course we will go ahead and rule out B and C. But this is a t-test, and I would say the most important thing for you guys in this section, even before you get your hands dirty with the computations, is to make sure you know when to use a z, t, chi-squared, f tests. Okay, so why is the degrees of freedom wrong? Well, because you are adding two sample size. Each sample will lose 1 degree of freedom, so this should really say 2 rather than 1. So you have to subtract 2 at the end rather than 1. So that makes statement B wrong. And statement C, when do we use the pooled estimate of the variances? So think of that. The pooled estimate of the variance is like a weighted average of the two variances. But when are you going to use that? You're going to use that if you assume that the sample variances are equal. But here clearly they're saying that they have different individual variances. So we're sort of assuming that each sample has different variances. So we're not going to want to pool them together and calculate the weighted average. We're going to probably just plug them individually into the formula. But as I said, the actual computation is not something you should be particularly worried about. Okay? Tough module, my friends. One of the toughest modules here in my course, but I hope you found it useful. I'm not going to be surprised if you need to watch this module a couple of times. Maybe after today, let it sleep, come back to it in a couple of weeks, see if you can solve the questions then again. But until then, thank you very much for watching, and I shall see you in the next module.